The topic of this talk is that sustainable solid-state recycling of metallic chips and thin pieces by thermomechanical consolidation or thermomechanical chip consolidation. This research on this has been going on at Northeastern University for several years, and so here, and also when I was at Shanghai University, we started to work on this, and our current project is more on powder consolidation, but in the future, maybe we could sort of extend to into this area. So here is a contribution from Sun Song, Yuan Pingyu, who are one is doctoral student, one master student, and Deliang Zhang was master student, graduate, and he also got Louis and Xiao Li contributing to the work. So at the moment, this become more and more important. We talk about now the like carbon emission, with countries to talk about to reduce the carbon emission, or like at least to decrease the rate of the increase of carbon dioxide emission to the atmosphere. In China, they say that by 2035 they get to the peak, and then by 2035 we get to the peak, and then by 2050 somehow we'll get to neutral, which means the emission of carbon dioxide will be equal to the intake of carbon dioxide by like biological, by other ways. Of course, that means that we have to reduce the amount of carbon dioxide emission, and of course, metals production and metal production account for about 8% of the energy consumption of the world, and which means because the majority of the energy is still produced by burning fossil fuels, which is producing carbon dioxide. So this drawing come from or flow diagram come from a paper by Professor Ravi and others from Germany, published in Nature in 2019, and so it shows the life cycle of steel and aluminium, which you can see is quite interesting. We know that the very starting point of steel making is to get the from earth, and then smelting to get pig iron. In previous talks we learned that, and then from the pig iron get into the oxygen-blown furnace, and to make steel, like by continuous casting slab, and then milling, like a rolling, or like basically rolling to get stripes, plates, or bars, or sections, and then coming to this, like say the steel used for construction, for railroad making, for making cars.
Sorry for the story, Professor Deliang. Are you
yes
changing the slides, or we can see only your first slide?
You cannot see the second slide?
Only the first slide we can see, not the second, the third, the fourth.
I see.
So it is stopped only in the first slide.
Can you see now?
We can see the slide, but are you changing the slide, or you are still in the first slide?
No, can you see the second slide?
No, not the second slide, only the first.
Okay, let me just. Very important paper by Professor Ravi and colleagues in Germany, published in 2019, and I just choose the diagram which shows the life cycle of steel and aluminium. For the talk later on, I'm also going to cover the aluminium. and I'm not going to cover the steel because we have not done much on this. But the general principle are okay, are sort of a common. From here, from this, the first diagram can see that the steel making utilize the minerals from earth, and then go through the pig iron, and then the furnace, like first within our project we had talks on this, and his last talk was about the steel making. So, and in this process, of course, at every step there will be some waste produced, and also when making the slab, there's some some waste, and like scales and things like that, and then further rolling into like a plate or sections or stripe, and then of course come to the next is manufacturing. Manufacturing for making different products, or also for different structure, like for construction, industrial equipment, vehicles, and other goods, metal goods. And so in this process, a fraction, maybe say 20% of the material would come into the scrap, because like when sheet metal making is scrap. And then of course when the products are made or structure made, some product and structure stay there for longer time, for long time, like the bridge might stand there for 100 years, and so still that was in stock, and so that's being used. But of course, also a fraction of the products come to the end of the use. The very a common example is the packaging material, like for packaging, like cans. Once the products inside the cans are used, they come to the end of the cans, and or like vehicles, after 10 to 15 years of use of the vehicle, or 20 years of use of the vehicle, they come to the end. So that means a large fraction, each year a large fraction of the metallic material will come to a scrap. For steel, there's a way of recycle the scraps. Scrap steel, say by furnaces, by melting, by arc furnace melting. Yeah. And then for aluminium, the story is the cycle is quite similar. Again, for aluminium, the construction, construction industrial equipment, transport vehicles, and others, and packaging. Like you can see, 18% of coming to wet packaging. So a large fraction of the aluminum is used for like a beverage cans. And but of course, many products they soon come to the end of the life and they come to scrap. And so the new scrap. So in other words, the scraps or the material come out of the manufacturing, come out of the end of the life of products. So the large fraction of that. So how we utilize that, so that we sort of like reduce the use of the mineral and also the energy, especially for aluminum. The energy consumption for making aluminum metal from aluminum oxide is very intensive. It consumes a lot of energy, very intensive. And if we use the metal scrap to make aluminum, the energy consumption is only about, I think, about 5% of the water used for making aluminum from alumina. So it's so the more we use that, the more scrap we use is better. So and so that's really the driving force. So if we want the metal industry to be more sustainable, we have to cut down the energy consumption, and also we have to reduce the resource consumption, natural resource consumption, because the supply of natural resource in the form of minerals is limited. So the Earth is only so large, and the population is increasing. So we really do that, because sooner or later we may run out of the supply of the minerals. Sooner or later, of course, now because of the extreme weathers, we see that we must act quickly for reduce the energy consumption, reduce the carbon dioxide emission to this. So it's become more critical. And just looking at the magnitude of the amount of recycled aluminium or recycled metal we will deal with, is virtually coming into hundreds of, sort of millions, if not hundreds, meaning tens of millions of tons of metals. I'm sorry for this in Chinese. Don't worry about the left part. If you look at the bar graph, this shows the recycled aluminium. Keep in mind that not all aluminium is recycled, but the rate of recycling of aluminium is quite high. As I think it's about 80% of the aluminium is recycled. So it's about 7 million tons and 7.15 million tons of recycled aluminium. The total production of aluminium in China each year is about 40 million tons of aluminium. So out of that, about 7 to 7.5 million tons of aluminium. Just quite high. And of course, if we look at the ways of aluminium recycling, there are two major ways. The major way, or the predominant way, the way which is being used now, is melting, casting, and then thermal mechanical processing. But of course, if very often the recycled aluminium is used to make castings, so just no thermal mechanical processing. And so the characters of this process is that the recycling rate is less than 100%, because some material is lost because of the oxidation of aluminium and also the inclusions, and also relatively high energy consumption. The energy consumption is for recycling aluminium is lower than making aluminium from alumina, but it's still pretty high. And another important is that the recycled aluminium alloys are considered to be downgrade alloys. So they are treated as a lower grade of secondary, called secondary alloy. Yeah. So this is a major. And now there's internationally there's quite a number of groups working on the new way of, or another way of recycling aluminium, called solid state recycling of aluminium alloys. This by thermal mechanical consolidation. In this one, there's no melting, and the recycling rate is close to be 100%, because we don't need to lose any material. So of course, realistically, a little bit of material will still have to be lost, because that's reality, but maybe say 1%. And much lower energy consumption occurred in this process, because we don't have to melt the material, so that we don't have to supply the heat for melting the metal. And so the amount of energy used is about, so maybe less than 50%. So the energy saving is about more than 50%. And also the smaller impact to the environment, and also maintain the grade, or even we can get the better material because of thermal mechanical processing. So if we look at the cost, producing the primary metal will be quite large cost because of the energy consumption. And if we do recycling, the material from the recycling it's slightly less because they consume less energy. But of course, the scrap still have to be paid. So it's not just the processing cost, also scrap cost. And but if we use the solid steel recycling, the cost will be even less. It will be less than recycled aluminum from melting and casting. This is the solid state recycling process. We collect the chips or thin pieces. The chips can be just coming from the factory directly, and the thin pieces can come from the scrap yard, because the scrap factory, scrap processing factory, say for example, when they get cars, they crush the body of the car, and because much of the cars is made of a thin sheet metal, so they shred metal and produce the thin pieces. Of course, they also like engines, big blocks of metal. For those blocks metals, we don't consider here, because block metal is easier for melting, and we don't do that. And then we do a bit of pre-treatment. It could be washing or degreasing, depending on the need. And then we compact the shapes or thin pieces into compacts. And then we can use the hot extrusion. So after hot extrusion, we can produce rod or slabs or profiles. For slabs, we can do further rolling to produce plate or sheet. The rod, we can do further drawing for producing wires. Or of course, we can also produce profiles like C-channels or tubes, which are directly used. Of course, have to be before they have to be cutted. Or we could do extrusion forging. So if we do extrusion forging, so later on I'm going to show you what is extrusion forging. And we can we produce a near net shape. Luis, can you see the cursor?
Yeah, we can see.
You can see the cursor, right? When I remove the cursor. Yeah. Okay, so near net shape components. And then after machining, get to the component. So this actually is even more attractive, because we can produce parts directly. And these parts can be used. So just to illustrate this process, so here is use 6603 alloy, which is the aluminum alloy which are used very widely for making extrusions for like windows or constructions. Yes, big fraction of aluminum alloys is used in construction. And here we compact it to produce a compact. And then just extrude it into a rod, or like here it's actually like little billet, like a flat rectangle cross-sectional billets with rectangle cross-section. And this one can be rolled into a sheet. Of course, these are the samples only made in the laboratory, so they're very small. And I also have a picture for the tubes, not shown yet. And we can also use this one to make parts, like this. Yeah. So today's talk, another alloy we studied is the A356 alloy, which is a typical casting alloy, and it's only got 7% silicon in it. So the principle of the process is that densify the chips compact to full density by applying pressure, so apply pressure by die pressing, and also break the surface oxide layers on chips. Here I just use chips as example, but it's the same principle applied for thin pieces as well. So chips by plastic deformation of the chips, and then rapidly establish metallurgical bonding or atomic bonding across the unit chip boundaries at the metal oxide and oxide contacts. Because this bonding are done through the diffusion. So when the two surfaces are in full contact, inner contact and establish atomic bonding. So that means they get a strength from it. So from this point, I'm going to introduce the actual experimental study that the laboratory has done. This just use the chips and they produce that as I shown earlier. And here, this is the metallography picture, the optical microscopy pictures for the microstructure of the material produced. So this is the longitudinal section of the billet. This is near the surface and near the central region. So you see the inner surface because of the larger amount of shear produced. So that you see the chips. You can see the chip boundary, and they are well aligned. And in the center, the amount of deformation is a bit less, but of course it's still nearly fully densified. Just we can see the boundary between the chips still clearly. So this before the heat treatment. For this alloy, we do heat treatment to increase the strength. Yeah. So it's called T6 heat treatment. And this T6 heat treatment involves solution heat treatment at 530 for 1 hour and water quench and then aging. It's a typical heat treatment for aluminum alloy for this alloy. And to this, after heat treatment, the grains become bigger, and it looks like the interface become less obvious. They are still there. And this is the three-dimensional shape. Three-dimensional sort of a presentation of the picture. You see, this is a transverse section. This is the longitudinal section. So it's like, you can see, if you like, it's like a wood, like a timber. You see this goes to this sort of a line of the shapes and the shape. And in the center, the amount of deformation of the be less. And this XRD pattern. So of course you're familiar with the XRD pattern. For this materials, the XRD pattern is very simple. Just show the aluminum peak, because the second phase, like silicon, this one is a 66-1. So the second phase is magnesium silicide, but the amount is so small, so we don't show any peak here. And there's a little bit of texture along the 200 plane. And see the see the hardness distribution, the hardness across the sample, and the fairly uniform, does not change much, and from the edge to the center, it does not really change much. Before the heat treatment, the material is quite fairly soft. The hardness is about about 47 HV, so the HV number. And after heat treatment, the hardness increased dramatically because of the precipitate hardening. So this is, of course, the behavior of this is the same as the primary alloy. And yeah, so this shows the aspect ratio of the grains. So there's a bit of elongation of the grains, and the cross section is more or less circular, and along the longitudinal section, there's a bit of elongation of the grains. That's because of the grain, the growth of the grain is being limited by the boundary. This shows the boundaries. Again, here you see the bright. Here the bright one is the aluminum oxide of this, and yeah, here we looked at this. This sort of like being etched way alongside the natural way here to show the boundary. And when we look at the mechanical properties of the material, this one is only the 66-3 alloy, and the material still behave in a ductile mode, and this show the effect of the strain rate. So the effect on strain rate is very much, it's quite normal, and with the here with the increase of the increase of strain, here somehow with the increased rate, the ductility become decreased and the strength is decreased a little bit. Yeah, and after heat treatment, of course, the strength increase, and the heat treatment, the strain rate is less sensitive to the strain rate. But overall, the ductility of the material is still quite good, both before the heat treatment and after the heat treatment. So this shows the fracture behavior after the T6 heat treatment. So it's still fairly ductile, and of course we can see the lamination of the boundary. And, yeah. But with the lower strain rate, it's less. Less fun. So we can see that the there's the alignment, like the chips aligned along the extrusion direction, and so we wonder what the mechanical property of the material like along the transverse direction, in other words, along the direction perpendicular to the extrusion direction. So for that, we study the tensile property, the mechanical property of the specimens cut along the transverse direction. So this, here the it's a video clips and see what they can play. Yeah. So here just show you the. Can you see the video?
Yeah, we can see the video.
I can see video. Okay. Yes.
Yeah, you can replay again. You can replay again, please.
Yeah. So so you see of course this strain rate is fairly high. So yeah, so it's cut. You see the material is sort of fractured. The fracture surface a bit flat. So here show the tensile curve, engineering stress strain curve, and get about 8%. And this is just a screenshot of the video clips. You see different point, and of course because the strain rate is fairly high. For normal tensile testing is very high, but for impact it's high. So you see that produces strain concentration, localization, and then just near here just the fracture. With the lower here, the test is done at a lower strain rate. Here it just so you see here this pull, and so here now it's the material is ductile. But from here you can see that even along the transverse direction, the material is still fairly ductile. But from here, you can see that the strain distribution is more uniform because the it's sort of like of course it's actually it has time for the localized strain to be released. Yeah, and this of course this one is have a lower strain rate, 10 to the -4. So it's much 2 orders of magnitude lower. But here of course it's lower, and let's play this. But here you can see the change is much, the pulling is slower. But if you notice, they'll still change. Yeah. Oh yeah. So it's just like it's so slow you don't see the notice. Yeah, here start to see the um, yeah, you see the localization starts from the surface and then sort of spread across the material. You know, the high strength spread. But the good thing is that because it can spread, so it does not have the fracture. And then it starts to have the localization. Yeah, then this and the material fracture at localized. You know, at the point or in the region where the strain localized. The strain is localized. Keep in mind, this one is a 2 order magnitude slower. So you can see this. Okay, so that I think does not show the fracture point, but here's from the screenshot you can see the fracture. Yeah, this to show this. So anyhow, along the transfer direction, the material still have the same strength. This is the material after T6 kitchen. The strength is still same. The ductility is decreased, but still has a substantial amount of ductility. And this one to compare the material property near the surface and near the in the center region. So the strength is very much does not change, similar. Just the ductility in the surface is a bit higher than the central region, but not too much higher. Yeah, and we also mix the A356 alloy and with the chips, with the 6063 chips, the 2 kind of chips into it to see how so the one is 10% of A356, another one is 20% of A356. So here, of course, we still can see the chip boundaries, and for the A356 alloy, we have the silicon particles clear, and it's there. And for this experiment, we use 2 extrusion temperature. One is 450, another one is 500. And so this shows the tensile properties. Again, the material is fairly ductile. So with 63 ductile, same as earlier. With the here it shows the effect of adding the A356. So 10%, 20%. When the amount of A356 alloy increase, the strength increase, but the ductility decrease. And because the A356 is stronger, and so here it's after, yeah, this after T6. Yeah, this one is the with extrusion temperature of this, and this one is extrusion temperature of 500. And again, it shows the with adding the A356 alloy, the strength clearly increased. This was the strength of A356. Yeah. And but the ductility is slightly decreased. Now, if we compare, this is to compare the recycled, the solid steel recycled aluminium before heat treatment, after heat treatment, with the corresponding this 66 with the corresponding cast alloy. You see that the strength is very much similar or slightly increased, but you see the ductility actually increased quite a bit. That means the recycled material has even better mechanical property. And this shows how the property change at different like a center. This one is the near the surface, and this is near the center, and this halfway. Near the center, so like the consolidation. This was also with the strength lower and the ductility lower. So that means near the center, the material is not as good as near the edge, but still generally it's still quite good. Yeah, this shows the fracture surface of this near the center region, near the surface, and halfway. So, and from this you can see the fracture of A356 region, and this shows the same as like just a screenshot of the tensile test specimen to see the necking. The same process also used to consolidate other alloys like aluminium 5 zinc 2.5 magnesium alloy, and this one, and this the tensile test. The heat treatment done is not not sufficient to make the alloys as strong as the standard. But in general, the material shows a good ductility, good strength. Yeah, and it's the here we use the aluminium aluminium garbage cans. The alloy is the grade is 3004 for the body and the cover, I think. So 5082, and yeah. So and use this chip to make the material this board like this with compact. And some preliminary mechanical testing been done and found that the strength of material is okay, but the ductility is not as good. We need to continue to work to improve the mechanical properties. So A356 alloy is a casting alloy. Normally it's used for making castings, and after machining we produce these chips. And here we use these chips to produce a part like this. And so on the top, it's only the hot pressings we call HP sample. And in the bottom, this plate is produced by the extrusion forging action. So the material, like with the pressure, the material flows through this. And so for this one extrusion, and this one extrusion forging. So when it comes to the cavity below, is the extrusion forging. And so down the XRD is quite normal. And this is the mark structure of the material. To show the silicon particles, and you find that with the extrusion forge sample, the silicon particles are finer and more uniformly distributed. And here is the HP sample, the hot press sample. The silicon particles are distributed not uniformly, and the particles are elongated. And with the extrusion forging, it's more uniformly distributed and finer. Right? And so this shows particle size distribution. The particle size is sort of very much similar. Of course, here for the extrusion forge, the particle size is clearly finer. Yeah. And this shows the EBSD RPF maps. So you see the grains in the extrusion forge section is actually it's a recrystallized grains. For metals, of course, with the when it perform at high temperature, when the deformation amount of deformation high enough, crystallize. And in a hot press one, it's deformed grains, deformed grains rather than recrystallized grains. And after T6 heat treatment, because there's a solution treatment at 430, the grains grow quite dramatically. But there are also some small grains. The small grains are sort of left in different places, and this shows the grain size distribution. So here the fine grains, coarse grain. And here we have the coarse grain. And in this alloy, after heat treatment, we have the beta double prime precipitates. So this is all quite normal for aluminium. So if we look at the mechanical properties, the extrusion forged sample has a higher strength, better ductility than the cold press one. Before heat treatment, after heat treatment, the strength is similar of the two, but the hot press material sort of fracture prematurely with a small strength, and with the extruded forged material, this can go beyond like 6%. Also, there's strength hardened, so that it's got. This shows the strength hardening rate. You can see that the hot press, the extruded forged material has quite high strength hardening rate. This also makes the material have a better ductility. And these are fracture surfaces. Fracture surfaces generally sort of except the hot press sample, sample after T6 heat treatment. The other three is a sort of ductile fracture, but the fracture surface of the extruded forged material is more is rougher, so it's sort of like, and this one is less. Yeah, so this is it's flatter, and this shows the longitudinal surface. So you can see the damage of the silicon particles. This is sort of quite normal for this alloy, because the silicon particle there is brittle, and the sort of there's a sort of a damage here, and there's a ductile fracture. So after T6 heat treatment, because the stress level is higher, so the sort of the cavities are bigger. Cavities bigger, and so that's very much sort of the work we have done. And there are also some work published with older work, because time limit did not show. But in general, basically say for aluminum alloy chips, we done this. In the abstract, I mentioned that we also talk about the copper. Actually, not copper chips, copper wires. And we have done some work on that. The results are similar to aluminum alloys, so because time limit I did not include here. And we sort of, as I mentioned earlier, it would be ideal to like forge this into cavities to produce aluminum part directly. And from the work we've done, to show that the mechanical property of the part is very good. So that means the part can be used directly. And from this, you can see producing the part is very attractive, because the chips are cheaper than buying the primary alloys, I think about 20% cheaper, and also the process consume less energy, and the material in the part, in the component, actually also have good mechanical properties when the condition is right, of course. So from that we can see we can make like a more complex shape. component. So this one is for like in aerospace, using aerospace. This is a wheels. So that's very much what the experimental research is out here. So in summary, by using the chip for consolidation and forming the chip, we can get the structure members like by extrusion, but we also can get components. And the mechanical properties of the materials in these consolidated material products are sort of comparable, or sometimes even better, those of coronic primary alloys. And keep in mind, the secondary alloys are a lot cheaper and consume less energy. And also the good news is that we don't have to downgrade the alloys, so they are still as good as. And the solid striking has the advantage of low energy consumption, high material utilization, and short manufacturing. And of course, the structures of the solid steel recycled and alloys have the unique characteristics with good interchip bonding, and the interchip boundaries contribute to growth. And now the group working on commercialization of this technology. So here I should mention that the same technology can be extended to the thin pieces and also extended to steel chips or cast iron chips. You know, the steel chips, the amount of steel chips, I think probably could account for more, I would say, probably several million tons in China. You know, of course, in Peru, India, also there are quite a large amount. In the world, it's quite a large amount. And at the moment, of course, the steel chips are just sent to the arc melting, melting for making steel. And so, if we can make the steel out of the chips, it will be fantastic. But the dilemma with steel chip is that it can easily get rust, because when the chips is kept in outside in air, it gets rust. So same as the way to reduce the rust, which can be easily done, of course. Yeah. So I'd like to thank the funding. Thank the collaboration with the colleagues from Shanghai University, and also the funding from Natural Science Foundation China and the Union Program. Also, specifically the funding for our joint project, which give us the opportunity to discuss this research here. CONCYTEC, the World Bank, and also CISIA. So with that, I'd like to thank you very much for your attention. Yeah, that's it. Luis, can you see that?
Yeah, thank you very much. Thank you, Deliang. Thank you for the excellent talk. Thank you for the excellent talk. No, now is the time for the questions. Professor Ángel Bustamante, do you have any question? Professor Ángel Bustamante? Yes, go ahead, Professor Ángel Bustamante.
No. My question is the Lamina 45 show for me. There is a colored spectroscopy, no? In the 45, see, yes. Yes, it's what the meaning EBC SD techniques ABSCP. What the meaning this?
Yeah, it's called electron backscattering diffraction. Electron
backscattering. Okay. Electron diffraction. Yeah. By scattering the diffraction. Yeah. Thank you very much.
Yeah, backscattering diffraction. So it's like by using the Paul figures, they produce the contrast of the grains. Yeah, it's virtually shows the orientation of the grains. So because different grains
Okay,
have different origins, so
perfect. Thank you.
Yeah, thanks.
Okay, any other question, Professor Ángel Bustamante?
Yeah, I suppose the you know, I'm like Luis know that when Luis at you know in the lab, I would see that's the group more working more like a structural properties, the structure of metals, and so this from this, of course, you also can see what we are, you know, the things we normally do.
Yeah, thank you. Dr. Narcy Boya, any question? Narcy Boya, Narcy.
Yes. Hello.
Yeah, hello, hi, Nancy.
Yeah. Actually, it is mentioned in the slide number 5, hot extraction. So it will come seed type or rod shape. So how it is will come based on that whether it is giving extra temperature or this one depend.
Okay, which slide, Nancy?
Second, fifth, sir.
Fifth.
Yeah, fifth one.
Yeah.
Sorry. Next.
So your question is how, you mean how we heat?
Hot extraction.
Hot extrusion.
Yeah.
Hot extrusion. Yeah, hot extrusion. I mean, what's your question? Hot?
Yeah, it is will come rod shape and seed shape. How it will define whether it is coming rod shape or seed based on that giving any extra energy.
Oh, you mean like when we do hot extrusion, you mean we have to consume energy? Would that be right?
Yeah.
Oh yeah. Sure. Yeah. Of course, the thing is that with primary metals, we also need to do hot extrusion. So the process is still the same.
Okay.
It does not really do more than primary metal. But the thing is, with the primary metal, we only do like a recrystallization to get you know, shapes and all that. But with this secondary, like with the chips, this hot extrusion not only give us a recrystallized structure, but also give us the consolidation, like the bonding between the chips. So
Okay.
yeah, the actually the mechanical forming. Sorry, I have not done any calculation here, but from the literature, the of course we can do the calculation if you want. The amount of energy consumed by mechanical deformation is much less than melting.
Okay. Thank you, sir.
Okay, thanks.
So, Professor Deliang, what I understand then it is that, well, you reduce energy on the fabrication without any heating, right, during the consolidation, right? Is that okay?
No, we do heat.
Yeah,
but that's what I call hot extrusion, and extrusion forging is hot. But we only, for aluminum alloys, we only heat up to say like 500 degrees. You know, when we do melting, because in the recycling of chips, they have to send it to melting plant. And in order to melt, we have to heat the chips to like 700. Yeah, the melting point in alloy, of course, is 660. So that means we have to reach that temperature. But that's not enough, because for casting, we have to make the liquid metal to be, say, at least 50 degrees higher than the melting point. So normally, we heat the liquid to 720. So that means one is 720 in comparison with 500. So that's already 220 degrees higher, which means you have to supply more energy to heat metal. But also,